All right, we are looking at problem number 10 from semester review 2. So we're technically on page 4.6. We're talking about a rational function. And the first thing I think you'll notice is that the top has 4 terms. So that eliminates most of the ways we know how to factor. That eliminates, um, you know, difference of squares, difference of cubes, sum of cubes, trinomials, and binomials. All that's really left is a common term, which we don't have a common term, or possibly by grouping. And luckily for us, we can factor this by grouping. The first 2 terms have a 2x squared, the second 2 terms have a negative 3, and so that's what we're doing in this step right here. And then what we realize, quite fortuitously, is that the 2 terms I have remaining both have a common factor, an x plus 4. So I can factor that x plus 4 out, leaving me with the 2x squared and the minus 3. And now I have the top factor. So had to go to factoring by grouping for that one. The bottom didn't need to be factored, and so really without even factoring the top, we could have done the domain. Remember, the domain is just going to be zeros in the denominator. Those are the only undefined values. So we can take that negative 4 out. Boom, the domain is done. But now that I have factored the top, I realize that that undefined value, which had to be either a vertical asymptote or a whole, is a whole because of the cancellation. So that's how I know there are no vertical asymptotes, and the whole is at negative 4 something, right? Negative 4 something. And so we get 3 of our steps done pretty much just by being able to factor our problem. Now, what is that missing, whole value right here? That is going to be something we have to mathematically determine. So I go to the reduced equation, and I think you'll agree that after these x plus 4s go away right there, that all I'm going to have left is a 2x squared minus 3. And I'm going to plug that negative 4 in. Negative 4 squared is 16. 2 times 16, 32. And it looks like after I subtract 3, I get a 29. And there's your whole. Negative 4, 29. Horizontal asymptotes exist if your function has converging end behavior. So we're going to have to look at the end behavior model to determine that. The power on the top is the x cubed term, and the power on the bottom is the x term. So 2x cubed over x is what I'm going to set up as my end behavior model, which is just 2x squared. Okay. By the way, this is 2x squared right here. Okay. It's a parabola, isn't it? 2x squared. So let's keep that in mind as we look at our function. The range is the only thing left, right, that I need to get. I guess I didn't finish my last thought. Because 2x squared has up end behavior, right, like a parabola, it doesn't converge, which means there are no horizontal asymptotes. So that's the link from our end behavior model to the horizontal asymptotes. Now we've got 4 of our things done. 1, 2, 3, and 4. The only thing we don't have left that we haven't done is the range, and that's the one that you really have to take a look at a graph on that one. Okay, so that's what we're going to do. We are going to go find a graph, and here's what I would see initially. Okay, which looks pretty much like the parabola we just looked at, but maybe I want to look at it, on a larger scale, because like the whole, I wouldn't even be able to detect that, because remember that was at negative 4 over here, and I don't even go up that high. So I'm gonna change my scale a little bit, and what we see is it really didn't change my graph that much at all. I mean, I do still have the vertex at 0, negative 3, and other than that, it looks exactly like the graph you would get if you graphed just 2x squared minus 3. Notice this is the graph of just 2x squared minus 3. Look at that. They're identical. They're identical to each other, except the 2x squared minus 3 is continuous, whereas the ugly function that we were looking at has a hole right here. Notice I I traced out to that exact value, -4, and it told me it was undefined there. That was just confirming that there is indeed, a little hole right here. We don't really see it, but that's where it is. Um, the other thing I did is I found the minimum value. It doesn't look like this graph ever drops below this vertex. And it turns out it's at exactly -3. We could have plugged a 0 in and figured that one out. It's just a shifted, when you looked at the end behavior model, a parabola that was shifted down 3 units. So it looks like our range, we can now figure it out. And what our range is going to be is all real numbers, starting and including -3, right? So that would be a bracket. And then going up towards infinity. Now, at first, we're like, well, wait a second. As I was coming up over here, I ran into a little problem at the height of 29, and so maybe I need to, take 29 out of the range. But if I follow that height across, we hit the same exact height at a different point on the other side at +4. And so that value does not have to be taken out. And that, of course, is what we refer to as covering the hole. And so think about that, the range from -3, including -3, to infinity. And sure enough, that is your range. So that was problem number 10, a rational function for your digestion.